The students in our college algebra class could basically be divided into two categories. Some of you have majors that involve science, technology, engineering, and math. You may find the information about complex numbers interesting. Some of you have majors that don't have anything to do with mathematics. Perhaps you're in this class because your advisor said you needed it for your degree. You may be thinking, why do I care about imaginary numbers? And that's okay. But let me ask you a question. How easy is it for you to turn the lights on and off in your house? Well, it's pretty simple. You walk over to the wall, you flip the switch, and the lights come on. Did you know that imaginary numbers are involved in the electrical circuits behind that process? Now, you don't have to know about imaginary numbers to be able to turn the lights on, but perhaps you can gain some appreciation for the electrical engineers that design our homes and our buildings so that we can use electricity safely because of their knowledge of complex numbers. In this video, we're going to take a look at some interesting applications of complex numbers, starting with electrical circuits. To represent the alternating aspects of AC circuits, alternating current circuits, engineers use complex numbers to capture both the magnitude and phase of an electrical quantity. Remember, in standard form, complex numbers have two components. Each component can be used to represent something significant. Ohm's law relates the current in a circuit, I, in amperes, the voltage of the circuit, E, in volts, and the resistance of the circuit, R, in ohms, by the very simple formula E equals I times R. In example 8, we're going to use this law to find the voltage of a circuit if I equals 2 minus 3I and R equals 5 plus I. So the formula that we're using is Ohm's law. E equals I times R. We're looking for the voltage E, and we know the current I. So we're going to plug in this complex number, 2 minus 3I, for capital I. And we're going to replace R, the resistance, with the complex number 5 plus I. If we FOIL these two complex numbers together, we end up with 10 plus outside terms 2I minus inside terms 15I, last minus 3I squared. When we simplify, we end up with 10, combining middle terms, minus 3I, minus 3 times I squared, which we know is negative 1. So that's 10 minus 3I plus 3, or 13 minus 3I. So each part of that complex number represents something important about the electrical quantity, the magnitude and the phase. And this is measured in volts. So the next time you turn your lights on and off, think about imaginary numbers. Another interesting application of complex numbers is with mechanical vibrations. For those of you going on to take our calculus series all the way up through differential equations, you may end up studying this particular application. Mechanical engineers use differential equations to model masses oscillating on springs. So if I have a spring, it has a resting position or an equilibrium position, but if I hang a mass on that spring, it's going to stretch it beyond its equilibrium until it comes to a new resting position. So this is going to be the new equilibrium position for that mass. Now, if we take that mass and pluck it just below its equilibrium position, the spring is going to want to go back to its resting position, so it's going to exert an upward force on that mass. When that compresses the spring again wants to return to its resting position, so it exerts a downward force on that mass. And then this continues, causing the mass to oscillate above and below its equilibrium position. It's a very simple model. That oscillation is what we call simple harmonic motion. Now, if damping or resisting forces are present, like gravity or some sort of shock absorber, then, surprisingly enough, imaginary numbers can be used to discern between systems that are overdamped, critically damped, or underdamped. So an underdamped system is going to have resistance, but it's going to continue to oscillate with an ever decreasing amplitude until it settles back to its equilibrium position. An overdamped or strongly damped system is going to settle down very slowly to equilibrium position. Or a critically damped means that it is going to gently settle down to equilibrium position without oscillation. So imaginary numbers are in the mathematics behind that mechanical system. Another fascinating application of imaginary numbers is with what we call a Mandelbrot set. The Mandelbrot set is a fractal. A fractal is a simple pattern that repeats on changing scales. For example, let's suppose that I start with a single line segment and I divide it in such a way, maybe about 2/3 of the way down the segment, and I construct 2 new branches coming out of that joint. Okay, it's a very, very simple pattern. Now I'm going to apply that same pattern to the 2 new branches that have been formed. So I'm going to go 2/3 of the way down this new branch and construct 2 branches out here. And this was a new branch as well. So I'm going to apply that same process over here. And again, anytime a new branch is created, I'm going to apply that simple pattern. So it's the same pattern, but notice the scale is changing, right? The size of those branches are changing. And we end up with what we call a geometrical fractal pattern. Kind of looks like a tree. There's many things in nature that follow a fractal pattern. One famous example of a fractal is this beautiful picture. That's the picture of the Mandelbrot set. This intricate and complex pattern is generated by the very simple equation z sub n plus 1 equals z sub n plus c. Z happens to be a complex number. Now, if you don't quite understand how this equation works, that's okay, but I want you to understand that you have such a simple equation leading to such complexity and beauty. I find that really amazing, and that's all based on complex numbers. So complex numbers are fascinating, and we have just begun to scratch the surface in our understanding of them. So I hope you enjoyed those applications, and I hope you all have a great day.